All right, well, the next section we're going to cover is 3.2 in your book. And that book is Discrete Math and Open Introduction. You can access that through their website. You can download the PDF. There's a link to it on the front page of your Canvas page. So we're going to start talking about proofs. And we're going to prove mathematical statements, the logical statements. And so the type of statements we're going to prove are if-then statements. So if you remember from our symbolic logic section, if-then statements are symbolized by P arrow Q, and we read this as if P then Q. So we're going to take specific statements, mathematical statements that we can decide whether or not they're true or false, put those in for P or Q, and then try to decide if the whole statement if P then Q is true or not. And the way we're going to do this is, those remember what the truth table looks like. Here it is. The only time we get a false for if P then Q is if P starts out, if P is true, but then we end up with a false Q statement. So the way we're going to prove these is actually sort of focusing on that point. And the line we're going to take, or the row we're going to take as our sort of template here is going to be this first row, which if P is true, in order for the whole statement to be true, and I guess the second row sort of as well, we need Q to be true. And so we're going to start here and then show that this must be true. So the method here, sort of general method, is assume P is true and then show, in the event that P is true, this forces Q to be true. And all the work sort of happens in between these two things, in between our assumption and our conclusion, which we hope is logically sound and says that Q is true. And so what happens in between this? Or how do we show that Q is true? So the way we're going to do this is we're going to translate our statements into algebra. So algebra is nice because it has, a bunch of nice rules, and it's, completely contained, and, everything you can do, you can undo, and and you can move it around symbolically. You don't have to depend on these sort of arguments in English. And so we're going to translate everything into algebra. Once we make a statement about P being true, we'll translate that P statement into algebra, do some algebraic moves. And these moves should show Q is true. And then translate it back to English and just make the statement that Q must be true. Okay. And so what does it mean to translate our statements into algebra? Okay, so the first few examples we're going to look at are going to be about odd and even integers. So first examples. Concern odd and even integers. So one example of translating into algebra could be, well, what does it mean algebraically for a number to be even? So we'll say A is even. And we'll say this is in English. Okay, so what does that mean in the language of algebra? So there's a lot of ways you can use algebra to say that A is even. The way we're going to sort of use over and over is that even is the same as being divisible by 2. And divisible by 2 is the same as saying I can factor A into 2 factors where one of them is 2. So for example, so this is how we would write it. A is equal to 2k and k is any integer. So for example, maybe we should put an example under here. Using the algebraic definition, I know that 50 is even, so that would be the English, because I can write 50 equal to 2 times some number. And it happens that that other number is 25. And so just the fact that I can factor this way is telling me that 50 is even. Okay, and so that's what we're thinking there. And then the other statement we're going to need to translate in the beginning often is that something like a is odd. And so what does it mean to be odd? Well, it means you're not even specifically, that you're not divisible by 2, but it turns out in algebra it's hard for us to say often that you are not something. So how can we do this constructively? How can we say something's odd in a positive way? The way we'll use most of the time is that every odd number is one more than some even number. And so we would write a is equal to 2k, which is an even number, but it's not an even number, it's one more than an even number. And then this is true for k, any integer. Okay, so what we're saying is that every odd number is one more than an even number. But this is a nice algebraic expression, and we can multiply it, and we can factor it, and we can do all kinds of things, which is going to help us prove these first statements. And so maybe we should do an example of this. So let's pick an odd number, like 17 is odd. And so what we're saying above is that if 17 is odd, I should be able to write it as 2 times something plus 1. And so what is that something? Well, I guess it's 8, right? So 2 times 8 is 16. And 16 plus 1 is 17. Okay. So in the next video, in example 1, we're going to do an example where we actually prove some statements about odd or even, and we'll see how these things come into play.